All right, welcome everybody. Let's get started. How many of you have Android phones? So you saw my message yesterday. It's such a bizarre thing because Cam Scanner is like one of the top apps in the entire Google Play Store, but it looks like one of their advertising partners snuck in some malicious code that would be potentially, I don't know if it actually happened, but potentially your phone could end up mining Bitcoin for someone. It's probably some disgruntled programmer at an advertising partner thought, I'm leaving, I'm going to get rich. And so anyway, for now it's been pulled, as I said in the message, and so until they get it all sorted out, it's okay for you to submit JPEG files, but it's not preferred because I have to individually download each page if it's a JPEG file, whereas it's a lot quicker to look at the PDF files. So, do you have a question?
Well, what if you already have Cam Scanner already installed?
So if you've already got it installed, you can feel free to leave it on, but if you are like super security conscious and worried that you want to cover all your bases and don't want even the slightest possibility of your phone mining Bitcoin for a disgruntled programmer somewhere, then my suggestion is uninstall it and then reinstall it when the program gets back on the Google Play Store.
Can you email us on that one or not?
Pardon me?
Can you email us on that, or we should drive?
Yeah, I'll send you an email when it's back up.
I think it came out with an update.
Okay. Great. So today we're going to be talking about compounding of interest. And the next homework assignment is available on MU Online. Did you notice it there when you uploaded homework 1? That homework 2 is available now? Okay. So you've got a week for that one. It's due on Thursday the 12th. And I wrote that homework assignment after looking at the problems I'm giving you for today's in-class exercise and Tuesday of next week. So if you're here and engaged and participating in these in-class exercises, then I hope the homework will just be smooth sailing. All right? Any questions before we start talking about compounding? I'm trying to remember if there are any other kind of general announcements, but I don't think so. All right, so let's begin by looking at an illustration that kind of refreshes your memory where we left off on Tuesday. On Tuesday, what we were doing is we were talking about this idea of how money moves through time and the phrase economic equivalence. And remember that the time value of money, and that's a really important phrase, time value of money. What that means is it's the idea that because prices are always going up, a certain number of dollars today has a different value than that same number of dollars or any other currency in the future. And so what this illustration, this is just a problem that is showing what if you were going to take out a loan and you received 4 payments in equal amount, so an annual uniform series of 12,500. So you receive 4 of those, and then at the end of the 4th year, you're going to have to pay back some future amount. The illustration I'm going to step you through kind of refreshes that idea that the amount you got in year 1, that's going to be subject to more years of interest accumulating. And so one thing we can do is we can treat each one of these as just a separate find f given p. And I guess maybe that's another point of refreshing your memory is these ratios that we talked about in the way of summarizing problems. Like right now, this is an f/a. Find f given a. But what we could do is if you ever feel uncertain, like I don't remember how to do an f/a problem, or I don't have the formula for it, or the table lookup factors, you could break it up into a series of individual find f given p. Because what you could do is you could say, here's the f, and so let's say that year 1 amount is a so-called p. From the perspective of year 1's payment, how many years into the future would we be compounding that interest? Well, we'd go from 1 to 2, so that's 1 year. From 2 to 3, that's 2. and then from 3 to 4. So that's 3. So if we wanted to find out how much we have to pay in year 4, just for that first portion of money that we received, what we would do is we would compound it 3 years into the future at 5%. So that's what this table is illustrating. So this table is saying that, let's look at the columns we have here. First of all, I equals 0.05. We've got a column for the years and the amount that we have received in a given year. And then this column of previous balance, what we're looking at is the total amount you owe to the bank in the previous year before the row that you're on. So for instance, at year 1, your previous balance was 0. You don't owe anything to the bank in year 0 because you haven't got anything from them yet. Now, at year 1, the amount that you've taken from the bank and the amount that's subject to 5% interest is $12,500. So you don't yet have to pay the interest for the amount in year 2 or 3 because you didn't get those amounts yet. You're only paying the interest on the amount that you've received. At the end of the period, so year 1, what we're talking about when we say year 1, and this is a tricky thing sometimes. The first year goes from 0 until 1. We call that period the first year, from 0 to 1. So the second year goes from 1 to 2. So at the end of year 1, so if I was going to ask you, get a sharp pencil and put your pencil down on the end of year 1, that would be maybe just barely to the left of the number 2. So that's the end of the first year. I'm sorry, excuse me. Year 1 is from 1 to 2. So year 0 was from 0 to 1. Now the cumulative amount owed is going to be the amount that you took from the bank and also the interest that accumulates. And so if we go through this process of year 2, the amount that we're taking is $12,500, but our previous balance from the amount that we had taken before is now $13,125 because it's the $12,500 initially taken and the interest. What you're doing is you're having to pay interest on the interest. And so at the end of the 4 years, the amount of that future value is $53,877. So that's kind of the long way to do it. Does anybody have their textbook with them today? All right, in the back of your book, will you look up the 5% table? If you've got your textbook, flip through the appendices, and you'll find several pages of factor tables, and look for the one that says 5%. So what we're looking at right now is an F/A problem. Find F given A. It's an F/A problem, and the interest rate is 5%, and the number of years that we've got is 1, 2, 3, 4. Okay? So n equals 4. So look for the column that says F/A, and you're on the page of 5%, and n equals 4. What do you find as the factor that it says?
4.3101.
Okay. So later on what you're going to see is that rather than having to go through and calculate like a long table such as this, there's going to be a much quicker way to find the amounts, and it's going to be as easy as just going to the right table in the back of the book and using this factor. And if you multiply 4.3101 times 12,500, anybody bring a calculator to class today? Good. An engineer should never go someplace without a calculator. You're better off walking around without your clothes than without a calculator. If you're going to be a real serious practicing engineer, your calculator is more important than your clothes. Right? Because you know how often you're actually freezing or something, right? Let's be practical. All right, so what is 4.3101 times 12,500? $53,876.25. That's pretty close to this answer that we got by doing the step-by-step approach. So this step-by-step approach is basically just showing what if you're moving each one of these loan amounts that you received into the future. But there is this table method that is a whole lot faster. The table factor that we looked up had 5 digits in it, 4.3101. So that means that our answer that we get is only accurate to 5 digits. 1, 2, 3, 4, 5. So we'd have to round off to the nearest dollar in this case. We wouldn't be able to predict the number of cents with accuracy. And so that's why there is a little bit of variation between if you do this on the spreadsheet versus if you use the table factor method. Okay, so let's define some terms. A little bit of vocabulary and terminology here. Simple interest is pretty uncommon, but still we need to know about it. Simple interest is when you don't have to pay interest on the previously accumulated interest. You're only paying interest on the principal amount, meaning the amount that you borrowed. So just as an illustration of the formula, the way that you would calculate the interest that you're going to have to pay to the lender, it would be the principal amount times the number of periods and the interest rate per period. So let's say that if you were borrowing $100,000 for 3 years, 10% per year, so P is 100,000, N is 3, and I is 0.1, then the repayment is going to be the principal and the interest. You have to pay back both. And so the interest amount is $30,000. Therefore, the total due would be the principal, the interest, $130,000 together. So that's simple interest, and maybe the only time that you're likely to get a simple interest loan is from your parents or someone who really likes you. And the banks, they don't really like you, but they really like your money. So they use a different kind of interest called compound interest. And the way compound interest works is that the lender gets more back from the borrower, and we'll see that in an illustration here. Compound interest, you're paying interest on the principal and all the accrued interest up to a certain time. So compare and contrast our formula here. Interest was principal, number of periods, and interest rate. But the idea of compound interest is it's the principal and all of the accrued interest plus multiplied by the interest rate. This formula looks more complicated than it actually is. Just in words, the way that we would describe this formula is it's the interest amount in a certain year. So I sub t means it's the interest amount that you have to pay during a certain time period. It's going to be equal to the principal amount, all of the interest from previous years, multiplied by the interest rate. So let's look at a comparison. That same idea of 100,000, 3 years, and 10% interest. But this time, instead of it being just simple interest, this time it's compounding annually. And so do you remember what was the amount due in the illustration of simple interest? It was 130,000, right? So if you have compounding interest rather than simple, the amount due in the first year will be 100,000 plus 10,000, so it's 110. So it's going to be the principal and the interest from the first year. And in the first year, your interest is only 10,000. But in the second year, things get a little bit worse because you're having to pay interest not just on the principal, but you haven't yet given the lender any money back. And so the way that they're thinking of it is now you don't owe them just the 100,000, you owe them 110,000, and so they want their 10% on the total amount you owe them, not just the original amount. They want to charge you interest on how much do you owe today. or rather this year. So at the end of the second year, it's $121,000. At the end of the third year, it's $133,100. And so you can see that compound interest is better for the lender because they are going to be paid a greater lump sum amount than if they had just charged you simple interest. So any questions about this idea? Simple versus compound interest? So what about this complicated formula that I showed you? How would we use that? So remember, the way in words that we translate this equation is we say the interest due in a certain year t. So if we wanted to find out in the third year how much interest is due, we'd say the interest due in the third year would be the principal amount of $100,000, and then all of the previous year interest's amount. And so the previous year interest amounts were $11,000, which applied in year 2, and $10,000. So if t is 3, we're going to find the interest amounts at year 1 through t minus 1. So that means through the second year, the first and the second year interest. So the interest amount in the third year of $12,100, we could calculate with this formula. Or you could just do it kind of like a step-by-step, year-by-year approach. And either one of those works. Another important distinction when we're talking about interest is the idea of nominal and effective interest. And this is another trick that lenders use to keep borrowers a little bit confused and paying a little bit more than maybe they should, or maybe more than they understand they are paying. So credit cards are kind of notorious for playing these games. And let me show you what I mean. A nominal interest rate is its interest that's compounded more than one interest period per year, but it's quoted on an annual basis. So let's say you have a credit card and they say it's 16% per year. But if it's compounded more than once a year, if it was compounded quarterly, meaning 4 times a year, then really what's happening is the interest rate is 4% per period. And 4% per period is not the same thing as 16% per year if there's compounding. So if there's compounding, then the 4% per year is going to have an effective annual rate that's actually greater than 16%. And let me just write that example out on the board here using this formula. If we want to find out the difference between the nominal interest rate and the effective interest rate, we can use this equation, and all of the terms are defined on the screen there. And so in our example, the nominal interest rate are nominal interest rate per year. So let's say you've got a credit card company that says they're charging you 16%, so that's 0.16, and it's compounding quarterly. So M, the number of compounding periods per year, is 4. Then we want to find out what is the effective interest rate. So the interest rate that's effective is going to be 1 plus R divided by M to the M power minus 1. So let's just substitute in 1 plus 0.16 divided by 4 to the power of 4 minus 1. All right, and I see your calculators out. Why don't you tell me what is the effective interest rate if it's 4% per period and it's being compounded 4 times per year?
16.98%.
Okay, can somebody verify that? 16.98%? 986%?
Should be 99, sorry, it was rounding.
This is about 986. Okay, so in this case, the credit card company's a little embarrassed at how much they're charging you. effectively, if you carry a balance on that card and the interest is compounding 4 times per year, you're actually paying 16.986%. And so the way that they kind of hide the fact that they're charging you that much is they quote it on an annual basis, even though it's compounding more than once a year. It's just like a sleight of hand. And so it's important for you to understand the difference between nominal interest and effective. We'll get some practice on the homework and the in-class exercises with that. Okay, so speaking of which, I have the in-class exercise here. Let me hand that out. You're going to need to apply the idea of the ratios that we learned how to translate cash flow diagrams into, find F given P. And so in the ratios, the first term in the numerator of the ratio is what you're finding. It's the unknown, where P would be the given. And so in this case, the formula that's shown on the screen is something that you'd use directly to find a future amount if the present amount is known. And so let's say F divided by P is 1 plus I to the n power. And so if you actually know an interest rate, because it's given in the problem statement, and if you actually know the number of periods and some dollar value amount for P, then to find the future equivalent, so the economic equivalence of it, you'd have P times 1 plus I to the n power. And then if it so happened that you actually knew F, but you're trying to find P, then you just simply algebraically rearrange that equation where you're dividing the F by 1 plus I to the n power, and now you can find P with that same expression. Okay, so let me hand out the in-class exercise.
Don't start. I know that's the case, so that's why. We want to right after the class. You need to leave camp with your mom. Look at me.
Okay, so on the first one, you deposit $25,000 into an account that pays 6.5% per year compounded annually. Okay, so in this case, the compounding period is the same as what the interest is being quoted. So the balance in the account after 30 years. So N is 30, P is 25,000, I is 0.06, and all right, let's see if we can get the solution for this one. Oh boy. All right, so you'll notice that what I've done is in the problem statement, I've labeled the variables, and this can be a good habit sometimes to try and translate a really long text statement into just the pieces that you're going to need to substitute into the formula later on. So here you can see we've identified the P is 25,000, the I 6.5%. It's asking what is the balance. That means we want to find a single value for F. And so we've got this formula given to us. F slash P is 1 plus I to the N. So if you calculate the ratio of the future amount and the present amount, that ratio will be 6.6143. And since we're calculating that ratio in our calculator, we really have unlimited precision. So you can report your answer to the nearest penny when you're doing these problems in your calculator. If you're looking up the table factor, then you're limited to the accuracy of your answer being limited by how many digits are in the factor table. And although here I've only written down 1, 2, 3, 4, 5, I didn't actually round off. You know, I kept all the precision in my calculator, and you round off at the very end. If you round off during each step of a problem, you're going to introduce a little bit of error each time. And so it's just better to do all the precision and then round off at the very end. And so by raise of hands, did anybody else get the same 165,354? Good, good, good. All right. Well, let's look at the second problem. You need to have 95,000 available, so that's a future amount that's identified by that phraseology. And we have n is 15 years. How much should you deposit now is meaning find P, and then interest 4% per year compounded annually. So again, I is going to be 0.04. What if it said 4% per year compounded twice per year? How would the problem be different if it said 4% per year compounded twice per year? How would we handle that?
Use 30 instead of 15.
Good. Yes, n would be 30 instead of 15, and then I would also be different. We would need to find out the interest rate per period. And so in that case, if it's compounding twice per year, then the interest rate would be 2% per year. So just to give you maybe a preview of where things are headed, if it's compounded more than once per year, what you do is you divide the interest rate by the number of compounding periods per year. But in this case, this is one of those easy ones. We're using the same formula though, so we have to kind of say the present value is unknown, the future value is known, 95,000. That ratio that we'd calculated, 1.8009, and additional precision that's still in the calculator, so that when I divide the 95,000 by that factor, I get 52,750 and 13 cents. Again, any questions about this one? All right, so the third problem has two approaches that we can use to solve it. Okay, the third problem, as I wrote on the board, you can solve this either by finding the interest rate per period for Plan 2. That's what I was just saying, where if it's quoting the annual interest but it's compounded monthly, then what we actually have is 7.25% interest, but then you divide it by 12 to find the interest per period. And then the number of years for Plan 2, the number of periods would be 12 times 10. So there would be 120 periods if you do it according to this first approach that I wrote about on the board. The second approach is that you can find the effective interest for Plan 2, and then the number of periods would be 10 still. So let's go through each of those methods, and I'll show you how we can do it. All right, so what I've got here on the screen is that Plan 1 is this simple one because it's annual interest and it's compounded annually. So we don't have to do anything special there. We're just finding some future amount. The initial was 125,000. We're going to calculate the ratio factor. And 1.075 to the 10th power means that at the end of 10 years, your amount has more than doubled. 2.06103 means that you have more than 2 times as much dollars at the end of the 10 years as you started with. So precisely how much do we have? 257,628. Okay, so Plan 2 is more tricky because of the compounding thing. So there's going to be 120 periods during which compounding occurs, and the interest rate per period is the 7.25 divided by 12. And so 0.00604 and so on. That's the interest rate that we're going to compound 120 times. So the factor is pretty close to the other factor, but it's not exactly the same. You know, if you look at this problem, maybe it's two different savings accounts, and the first bank says we'll pay you 7.5% interest, but we only compound annually, and the other bank is saying, well, we may not pay as much, but we compound more often. So they're trying to maybe convince you to go with them because though they don't pay the same interest rate, they're compounding more frequently. And so what we're trying to do is figure out which bank is going to earn you more money when you compare apples to apples. You know, when you somehow account for the fact that Plan 2 is offering an increased compounding frequency. So what you'll see is that the future amount with Plan 2, it's pretty close to the same, but a little bit different. It's actually about $100 less. If we find the difference between the two, Plan 1 is more by an amount of $99.92. Now, the other way of solving this, like I wrote on the board, is you could calculate the effective interest rate for Plan 2. And let's do that. Let me show that on the board. So the effective interest rate, I effective, is 1 plus I, so 0.0725, divided by the number of compounding periods per year, which is 12, to the power of 12 minus 1. So the effective interest rate for Plan 2, it's 7.25%, but then there's also the effective compounding. So effectively, it's 0.074958. So once you calculate the effective interest rate, then you can calculate the future amount by just compounding 10 times. So it's kind of like you don't have to compound every month if you determine the effective interest rate. Now that you found this effective interest rate per year effectively, then we say it's 1.07498 to the power of 10, and that's bringing the factor to 2.06023, and so the finished amount is $257,529.02. So it's the same number, just calculated slightly different way. So you either have to have n is 120, and you use the interest rate per period, or you use n equals 10, and you find out what is the interest rate per year. Does that make sense to everybody? Okay. Very good. On the back side of the paper here, I'm going to pause and give you some more time to work on these problems. I'll circulate around, and if you want to check your work, I've got the solutions here. All right, I've got the amounts for problem number 4 up on the screen if you want to check your calculations. So if you have a credit card that pays 24% per year, then on a quarterly basis, that means it's 6% per quarter, and then you take it compounding 4 times. So it'll be effectively 26.25%. The idea is that when you compound more frequently, the interest rate goes up. So if you're compounding monthly, now that same 24% becomes 26.82%. So more frequent compounding is worse for you, better for the credit card company. But the increments are getting smaller. If they compound daily, it's not like the interest rate goes from 24% to 80% or something. There is an upper limit to the effect that this increased frequency of compounding can have. So on a daily basis, it would be effectively 27.1%. All right, problem 5 has two. Let's look at it first of all this way before I show you the solution. So problem 5 is just saying, give me the cash flow diagram. Don't actually solve it. Okay, your uncle's purchasing a delivery truck and will earn $247,000 each year for 5 years. Okay, so on a cash flow diagram, if you're earning money, is that an arrow up or an arrow down? Up. Anytime you get money, if it's coming to you and you're drawing the cash flow diagram from your perspective or your uncle's perspective, it's an arrow up. Okay, so this is an annual series. There's 5 arrows that are up. And what we assume is that your uncle is going to be earning the money and he receives it at the end of the period. So you do your work for a year and then you receive the income from that work at the end of the period. So for instance, if this truck is put into service now at year 0, the revenue from that year of effort comes at the number 1, meaning the end of the first year. That's called the end of period assumption. Okay, so we've got that annual series and some costs though. An overhaul at the end of the 3rd year, so that's a future amount of $55,000, and then we have annual fuel costs of $45,000 per year. Those fuel costs are going to be an arrow down. Now, it would be okay, but not preferable if you found the net annual amount. Like if you said $247,000 minus $4,500 and then you put that net amount on your cash flow diagram, that wouldn't be wrong, but it's preferred to actually leave each component in place so that you can see the individual contributions to what's going on in case something changes. In case the fuel costs go up or in case you want to adjust what your estimations are. And then the end of the 5 years, you have a future value of $95,000 because the truck is being sold. So the interest rate is known as 4%. We have an unknown here. How much should your uncle be able to afford to spend? All right, so here's how I expressed it. We've got the unknown is a dashed arrow down. We're trying to figure out how much can you pay now to be equivalent to all of these amounts in the future. Like what's the amount that would put everything into balance? So that if your uncle spends less than whatever we'd calculate, then your uncle's going to make a profit. But if your uncle spends more on the truck than this amount that we found, then there isn't going to be a profit. So that amount that you're calculating it's the dividing line between operating at a profit and operating at a loss. So we've got 2 different annual series, and it's good if you can to try and make the arrows approximately to scale, but don't lose any sleep over it if it's not. $247,000 versus $4,500. That's such a big difference in amounts that the arrows going down would be almost invisible, like if you were going to draw it perfectly to scale. So I just made it a little bit shorter to illustrate that it's less money. The future value, you'll notice I put a little bit of a gap between the annual series and the future value just to make it a little bit more distinct and visible. And it's important to put the labels on as well. So we've got an A, another A, a couple of F's, and we're finding a P.
But the $55,000 go on before because it's the end of the 3rd year?
All right, so the end of the first year is at 1. The end of the second year is at 2. The end of the third year is at 3.
Okay.
So I think it's in the right spot. It's tricky, but it'll get natural.
Okay.
Yeah. Are there other questions? All right, so this last one, you're going to calculate the amount using the equation method. And so what this is saying is that the ratio of A to P is this. So if you calculate this, it's the ratio of A to P. So that if you want to find A, you'd multiply P by whatever factor you calculate here. Okay, so let's see that amount. Okay, the P is 27,500. Interest rate of 9.5%. Okay, now you'll notice on the I, it didn't specify the compounding, did it? If it doesn't specify how frequently it's compounded, the default assumption is it compounds annually. Okay, so if it said compounds monthly or quarterly, then you need to make the change. But here we leave I as 0.095 because the default assumption is that you've got annual compounding. Okay, so you calculate the factor and leave as much precision as you can so you're able to report your answer to the nearest penny, and it should be $3,512.95. So that's the payment amount each year for it to be equivalent over the course of 15 years. Any questions about this sixth problem? All right, my suggestion, while this is fresh in your mind, you're never going to be more efficient than right now to work on the homework assignment, because this is all fresh in your mind. We just talked about it. You just finished your in-class exercise. You've got the paper to take with you, so if you can't do it like right immediately, at least you've got kind of your reference available. But maybe it's a good idea to start on the homework early so that you can just get through it when it's going to make the most sense to you. Let's take a look at the announcements before we finish up for today. All right. I think really the only thing on your plate right now is the homework assignment. Yeah, it's due on Thursday, a week from today. So if you have questions, feel free to stop by. I'd be glad to see you during my office hours. Other than that, have a great day.